you. Well, everyone in this room is very grateful to the organizers. I'm not an exception, so I would like to start by saying thank you to everyone, especially to Dmitri. Well, then I announced this talk. I realized that probably, well, the first two items do not tell you too much, and probably the third one tells you too much, so that relation is not really clear. And this is going to be actually, the content of my talk. I will show that actually Poisson sigma models and Poisson diffeomorphisms are very useful and very important to understanding the holography in 2 dimensions. And so to announce the result, you heard many times already in this workshop about the JT model, and it is holographically equivalent to many good things. And I'm going to show that not only the JT gravity, but also many dilaton gravities in 2D are also, well, holographically equivalent, at least to SIK in certain limit, through the Schwarzen action on the boundary. So that's this plan in more detail. So it was shown quite some time ago that the simplest dilaton gravity in 2D, Jackiw-Teitelbaum model, admits a holographic description quite classically, so this is a result in classical physics. It has Schwarzen action on the boundary, and Schwarzen action in turn is a certain limit, kind of quasi-classical limit, of the SIK quantum mechanics, which is extremely exciting result, not for me, but to many people also. Well, but then question arises, so that's JT model is well, extremely simple. It just allows you solutions which are at least locally ADS2, so it can have horizons, but it cannot have Cauchy singularities. It cannot have flat limit, and so on and so on. So what can we do? Can we actually extend this result to the models of different type, not having, let's say, ADS2 asymptotics or DS2 asymptotics or flat asymptotics, and actually we'll be able to do this with models which have practically arbitrary asymptotics, so any space can work. Since the dilaton gravities in 2D are particular cases of a very large family of 2-dimensional sigma models, which are Poisson sigma models. Poisson sigma models, meaning this is 2D, and they have a target space which is a Poisson manifold. It seems that the Poisson diffeomorphism, which make changes of coordinates on your target space, is a suitable tool to do that kind of calculations. Okay, so this is based on the work, so you see it was published 2 years ago, so it's not very fresh, and done with Daniel Grumiller, his student Florian Ecker, and Carlos Valcarcel, who was my postdoc, and he's in not far away from here in Bahia. So let me remind you what the dilaton gravities are. So that's dilaton gravities. Well, do you see this, by the way? Okay, fine. So that's they are written. So in the second order formalism, they are written like that. So the action is of course d squared x. Well, there is a usual term which is x. This is a dilaton field. Sometimes it is denoted as e2 minus 2 phi, e2 minus plus 2 phi, or whatever. But I prefer to use this parameterization, which is not exponential. Since this term, so this dilaton field has canonical dimension 0 in 2 dimensions, it's kind of natural to add to the action some functions of this x. One is just the usual kinetic term for the dilaton, which is multiplied by u of x. U of x can be anything. And okay, since you have kinetic term, you can also add some interactions. Again, in 2 dimensions, it can be anything. In most of the examples, this is just also exponential. And for the JT model, what you have, so you don't have any potential u here, so you don't have any kinetic term. And the potential v is just minus x, so that you don't have the second term, and the the equation of motion which you obtain by varying with respect to x will be curvature equals to 2. So that curvature equals to -2. So this is ADS to space for Lorentzian signature, or this is a hyperbolic space for Euclidean signature. So now we would like to make some generalizations, and the reason for generalization is the following. So before doing that work, so we wrote a couple of papers with some people from the same team, where we tried to work out some simple examples. And what happened that the most general result is the most simple one. So particular cases are much more complicated to do than the absolutely general case. So to consider the general case, let's do their generalizations. To do the generalization, first of all, we transform this action into the first order form. So the transform into the first order form is usually in gravity. So if you'd like to obtain first order formulation of gravity, you introduce an independent spin connection. But since the Lorentz group is one-dimensional in 2 dimensions, this is just a one form omega. And also you introduce 2 auxiliary fields which will generate you the torsion constraint, which will eliminate this, this new degree of freedom. And after doing this, we arrive at 2 first order actions. Now they look a little bit different for Lorentzian formulation and for the Euclidean formulation. So what is contained here? So this is the term which was dilaton times the curvature. So now curvature is just plus some terms. It's just the exterior derivative of one term omega, of one form omega. These x plus and minus guys are these 2 auxiliary fields which basically generate you torsion constraints. So if you vary this term with respect to x plus, you will get more or less the condition that this is now it's Weinbein, so this is not a metric. We cannot use metric anymore since it's first order formalism, that this Tribein is covariantly constant, and then you go back to the metric formalism. This is a similar term for x minus, and here you have a volume form multiplied but by some function of x plus, x minus, and x, which follows from the previous slide. So this is algebraic manipulation. Is not exactly straightforward, but it is doable, so that it's explained in a couple of pages. In first order Euclidean action, it differs a little bit, mostly because in Euclidean space it's natural to use components like 1, 2 instead of light-like components plus and minus. So, but basically, it's the same structure. Well, now look a little bit closer at these actions. What do we see? In the game, we have dilaton x, which is a scalar field, which is a 0 form. We have x plus, which is a 0 form, x minus, which is a 0 form, and more or less the same structure here, x, x1, and x2. And we also have 1 forms, so omega and Zweibein. Zweibein is a 1 form. And what do we see? So in each of the actions, we have x times exterior derivative of 1 form, x plus times exterior derivative here of 1 form, and the same guys here. So this is the general structure of the action, and a part of that we have terms which are quadratic in these 1 forms. So we have this exterior exterior multiplication 1 form times 1 form, 1 form times 1 form, and the volume form. So if at the first step you just would like to economize the paper, you can write it shorter, like the following. So you have 3 scalars, 0 forms, and 3 1 forms. Yeah, sorry, I integrated by parts here. So this is 1 form times exterior derivative of scalars, and some structure which is multiplied by the quadratic forms here. Okay, so at the first step, you can just try analyzing this action, analyzing the consistency, analyzing constraints, quantization, and so on. And what you will see almost immediately that this action is consistent only if this Pij satisfies the Jacobi identities with respect to the coordinates x, x plus, and x minus. So then comes interpretation. So there's x, three components x, x plus, and x minus, or x, x1, and x2 are coordinates on some Poisson manifold, while this Pij is a Poisson structure on this Poisson manifold. So this is more or less how Poisson sigma models were created by Scheller and Strobel, and also by Ikeda. So it was a generalization. So at least Thomas told me that he was just looking at the models, and he decided, okay, I can write it shorter. And then he studied the gauge symmetries. After being created, Poisson sigma models were used in many contexts. So for example, quite famous use of the Poisson sigma models was that Kontsevich formula for star product and deformation quantization can be obtained as a path integral in Poisson sigma model. So it's universal structure, and I believe that this is the only consistent, well, the most general consistent topological two-dimensional sigma model. So that's like that.
Identity, what happens?
Yeah, if you, this Jacobi identity guarantees you the presence of gauge symmetries. So if you don't have gauge symmetries, that means that including here the interaction just changes the number of degrees of freedom. That, roughly speaking, that. Or you can also analyze the constraints, and you would see that there are certain inconsistencies. So they create constraints to constraints, and they kill the theory. But basically it's that. So you have, obviously we have gauge symmetry in this term, which is just, well, usually abelian gauge theory. So this is, well, yeah, clearly it's part of electrodynamics. Basically it's BF action. And then I go here. Yeah, since these guys satisfy the Jacobi identities, one can show that these are gauge transformations of the Poisson sigma model. So they leave the action invariant, but well, I need a word of warning. So this gauge transformation actually close only on shell, and non-closure on shell is second derivative of the Poisson structure. So there are peculiarities of using this model. So quantization goes not so simple, and the reason is clear. If this guy here is linear, then this gauge transformation means, so it's linear and x, so variation of x some matrix linear term lambda. This is just a usual Young-Mills gauge transformation, and this guy is also usual Young-Mills gauge transformation of the field. So there is no problem at all if the Poisson structure is linear, but there are certain problems if the Poisson structure is non-linear. Okay, it's a generalization of a BF theory to a nonlinear case. Okay. Well, we have a target space which is a Poisson manifold. Since it's a manifold, we can use, we can make diffeomorphism transformation there, but we would like to make Poisson diffeomorphisms mean that they can preserve, they preserve the Poisson structure in the sense that they move one Poisson tensor to another. Or in other words, we change the coordinates and we transform the Poisson structure in the correct way. So what we are doing, diffeomorphism, as I already said, these x's are coordinates on the Poisson manifold, so they transform to other coordinates. This A, well, it contains an index ij, which is down, so it should transform something like that. And this is a good guess. It's indeed it preserves the form of the action, while the Poisson tensor is actually bivector, so it should transform as a bivector. So it transforms with two Jacobins. Well, of course, you may be skeptical, but you can also take these transformations, put them into the action, and change it as really invariant. It's invariant up to some boundary terms, but well, you usually have to integrate by paths to show that kind of things. What is also interesting, so it's not like Young-Mills. If you make changes of the basis in Young-Mills theory, you basically transform to Young-Mills theory, and also you transform gauge transformations to gauge transformations. It's not the case here, by the way. So the gauge transformations in the new model are not the gauge transformations in the old model. So this is kind of peculiarity in this seemingly very simple system, but well, so to make quantization you have to use quite a nice method like the RST. Oh yes, I forgot to say some words about that gauge transformations. So the initial model, which was a dilaton gravity, let's say, in the first order formulation, had the symmetry, so diffeomorphisms of the world sheet, which is the usual stuff for gravity. And also, since we use the first order formalism and independent connection, there was also Lorentz transformation. On shell, so new equations of motion, these transformations actually become that. So it's Lorentz plus a diffeomorphism, but away, so not on shell, again, they are not. So what's the idea? Now in more detail. To find a holographic dual in this classical setting to some two-dimensional gravity, well, what you have to do? First of all, we have to define a family of asymptotic conditions, which will depend on some number of fields living on the boundary, and which are going to describe you the boundary degrees of freedom. And also we need a boundary action such that with these asymptotic conditions, this boundary problem is consistent. So if they make variations, we do not generate new conditions on the boundary. And then also when we analyze asymptotic symmetry algebra, which is typically the part of the gauge symmetries which has been violated by our asymptotic conditions, we would like to get something interesting. Basically, we would like to get a Virasor there and maybe something else. And then, so if you have 1 and 2, so the last step of analyzing this thing is to take our asymptotic conditions. Since this is a topological theory, you expect that the full action for asymptotic conditions will be just the boundary action. Look at this boundary action attentively and separate something interesting, which we again expect being a Schwarzschild action in terms of these asymptotic fields. That's what we should do if you would like to analyze holographic duals to dilaton gravities. Well, the problem is actually with the first step. So you have to guess a little bit too much. If you would like to get interesting, well, large asymptotic symmetry algebra, you need very relaxed boundary conditions, so you should allow asymptotic conditions a lot of fluctuations. But in that case, you probably will get the boundary value probably which is inconsistent, since you have too many variations. And besides of that, probably you will have also the classical action infinite. You can try to cure this problem by introducing some holographic counter terms and so on, but actually this is a tough problem, since the usual if the space is not ADS2, then the usual rules by Pfeffer and Graham just don't work. So you have no idea how you expand your fields around the infinity. But using the Poisson diffeomorphism, we can actually map fields from one model to another model. And if they do the same stuff also with the asymptotic conditions and with the boundary actions, then definitely we will arrive at a consistent boundary value problem. since, what would we do? So we just, so we had an action which was written in the letters X and A, and we will have action, it's the same action, but written in terms of the X bar and A bar. So they're not doing anything essential. Diffeomorphism by definition is invertible, so it's 1-to-1, and the condition of extremum for one action is exactly equivalent to condition of extremum to another action. Also, since the boundary degrees of freedom are going to be the same, the asymptotic symmetry group is also going to survive. The only problem with us is to solve that, so to find a Poisson diffeomorphism which you need to fulfill this purpose. Well, it is going to be a little bit technical, but just on this slide. So when we analyze classical solutions, so these all the models, so all the Poisson sigma models are actually integrable. So you can at least the ones corresponding to TT gravities are classically integrable. You can find classical solution in a closed form. So there is just formula. So metric equal to this, dilaton equal to that. But the solutions are written not in terms of the potentials U and V. Instead, you need some other letters. And these other letters, well, are these Q and W, which are obtained by integration of this stuff. So in terms of the theory of ordinary differential equations, that means we have integrated functions here. So they look like integrated functions. And using these guys, yeah, you don't have to actually analyze or try to understand this formula, so they are as they are. And there is this quantity C which plays a very important role. So this is a combination. So this is function, first of all, it's function just of X. So there no A is appearing here. This is function on the Poisson manifold. And this function is constant on all solutions. If you calculate the derivative of this function, then it identically vanishes due to the equation of motion. So the time derivative and space derivative of this function are identically zero. Well, this is a Casimir function in this case. Well, and there is another property which is also, you should believe me, you have no other choice. That if you write metric in terms of these functions, then the Killing horizons appear at some points. There are these functions. So for Lorentzian case, this function W equals to C or X plus X minus equals to 0. So that we will use later. Well. Now a little bit about the structure of the Poisson manifold. It's a three-dimensional Poisson manifold, and all Poisson manifold can be foliated with symplectic leaves. Symplectic leaves are the guys to which the Poisson tensor is tangential. So there is this guy with two indices, and probably you can try to integrate this distribution in such a way that at each point of these symplectic leaves, Poisson tensor is tangential. Or in terms of the dynamical system, that means that all Hamiltonian vector fields belong to the tangent space of these leaves. So this theorem is always possible. These leaves are symplectic manifolds, so there is a non-degenerate symplectic form, which is projection of this P to symplectic manifold. Therefore, they are even dimensional. So all symplectic manifolds are even dimensional. For dilaton gravities, the target space itself is three-dimensional. So the symplectic leaves should be either zero-dimensional or two-dimensional. And since we have this function C, which is classically conserved, it also have a step to show this function has vanishing Poisson brackets with all the variables, so it's constant on all symplectic leaves. So to find this symplectic foliation, they basically have to analyze the equation C equals to constant. So all symplectic leaves are subsurfaces. There are this integration function, well, is some constant. For let's say for JT, as I said, JT, there's a case when we have a very simple Poisson structure, which is linear. So this is basically a Young-Mills theory, which is everyone knows is a BF theory. Well, it's very easy to compute this function. And for Lorentzian signature, this is just a product x plus x minus and 1/2 of x squared. So this is just a Casimir, just a usual Casimir in terms of finite dimensional Lie algebras of SL2. So if you write x plus x minus like x1 minus x2, x1 plus x2, you will get just a Casimir, just usual linear quadratic Casimir of SL2. Well, what are the symplectic leaves? If C is positive, then it's easy to understand that this is to each C positive there is a single symplectic leaf which is just a one-sheet hyperboloid. So these are all equations of hyperboloids, and these symplectic leaves always contain points there x plus or x minus equals to 0. Since if this guy is positive, then there is a solution for x. So that means that C positive for the JT models correspond to solutions with horizons, so kind of black holes, although there are no singularities. If C is negative, then the horizon points are not included, so there is a configuration without horizons, and these are two-sheet hyperboloids, so this is things like that. And for C equals 0, the situation is a bit more complicated. Well, there are cones, but cones are not manifolds, they have a tip. Tip is a zero-dimensional manifold, zero-dimensional symplectic leaf corresponding to all guys equal to 0. And the rest are just cones without tips, they are manifolds. So this is the structure. Well, why are they analyzing this? Because it's clear if they make a Poisson diffeomorphism, so if we just have one Poisson manifold and other Poisson manifold, each of them has its own structure of symplectic leaves. Then clearly we'll have to move symplectic leaf to symplectic leaves just because we move Poisson tensor to a Poisson tensor. So already here there is quite simple geometric picture of what we would like to do. So we would like to do some maps between two manifolds such that its foliation is preserved. But it's still too much, so it's not clear how to do that. So there are two-dimensional leaves here, two-dimensional leaves there, and it seems that there is too much freedom. That's first of all, and it's to less clarity. If you would like to come from one model to another model, you don't know how to do that. Well, it was a part of our frustration for some time, but what came out that the solution is extremely simple. So suppose for simplicity that you have a JT model with that symplectic leaves which are described by hyperboloids, and you have some other model which is described by whatever. And you're asking yourself whether you can find a diffeomorphism which maps JT exactly to that guy. And the answer is, locally, the answer is positive. Locally means the following: you can solve the differential equations which describe a diffeomorphism. They are differential since, look, the Poisson tensor transforms with derivatives. And this is how derivatives come into the game. So these are partial differential equations, look complicated, but the solution is simple. What do they do? So the quantities with bar are quantities for a new model, and without bar, this is what we have in JT. X, so the dilaton is shifted by some function, which is a constant on each symplectic leaf. So this is function of C. C numbers your symplectic leaves. X plus and X minus are transformed in here in a not too symmetric form, but this is because I of course know, so I need a dilaton gravity, and dilaton gravity has a Lorentz symmetry. So for Lorentz symmetry, I can always make a Lorentz transformations which are different for X plus and X minus, and just say, okay, this guy doesn't transform. It's not necessary, but it makes formulas a little bit easier. And here is, well, a bit more complicated stuff. But what is important for us is that, again, it depends on just one arbitrary function, and this arbitrary function, again, depends on C. So whatever happens here happens uniformly on the whole symplectic leaf. That's, well, it might have been expected for, well, more educated persons. I wasn't there. What is interesting? So what is the meaning of these functions? Now we can compute just from the canonical formulas, which I gave before for U and V, U bar and V bar, the conserved quantity in the new model by using this transformation. So they put files and these entities inside, and we see that this conserved quantity in the new model is just these two functions, that function G2 of C. Okay, so that's, I'm still describing the situation. And there is another point here. No, I have to go back. There is something a little bit dangerous. So there is one of the x plus at this point, and it's multiplied by something. So that means that x plus equals to 0. We would like to avoid infinity, and to avoid infinity, we have to impose a constraint on G2. So on where x plus equals to infinity, this function equals to that function. Okay? But now let's remember, so that x plus equals to infinity, or x equals to 0, or x minus equals 0 is a horizon points if they are. So this is a condition on the horizon points. So it's written in more explicitly here. And now let us see what is actually going on. So there is, first of all, let's analyze one of the functions. You see these functions, C bar is a function of C. So that means, so this just tells you how you arrange your symplectic leaves in the model to which you are mapping. So you have a stack of leaves, okay? Let's consider planes. And you have stack of leaves here. So you map this to this, this to this, this to that. And that's what it's saying. And also it's telling you that you are completely free. So you can do whatever you like. You can make map the leaf which appears at the point 1/2 to 1, 3/2 to 25, and you can do whatever you like. Yeah? Except that this function G2 has to be invertible, so that means it has to be continuous and monotonous, nothing else. And there is another function. This is G1. What does it do? So this function shifts the value of a dilaton such that the horizons coincide. Okay, so the horizon here should be to point the horizon here, and it's over. So if you have the structure of symplectic leaves, and symplectic leaves are solutions of algebraic equations, so they are quite simple. And if these symplectic leaves have the same topology, I mean, one sheet hyperboloid has a topology of a cylinder, two sheet hyperboloid is a plane. So if you have planes here and planes here, you can map one to the other in just any sequence you like. It should be just monotonous, so you cannot change the order of the leaves. So you cannot move this here, here, and then suddenly get here, because the function, it wouldn't be a diffeomorphism. If additionally to that, your symplectic leaves have horizon points, so the x plus x minus equals to 0, you should match them. So you have a horizon point here, here you move one leaf to another, and then use another function to make these points coincident. And this is over. I mean, if you have that structure of symplectic foliation in two Poisson sigma models, they are related through a Poisson diffeomorphism, and therefore there are a lot of equivalent statements there. That's it. Okay. If you need explicit formulas, you have to work. So these all guys satisfy certain equation, and yeah. If this are even, well, polynomial equation of order 5, well, you're lost. Okay. Now about examples. So one of the examples is also extremely simple. Well, there is a model, yeah, that's probably known to many of you. It's CGHS, Color Genius Harvey Strominger, which came with certain stringy motivations. So it describes string Black holes. On itself, it's a little bit complicated, but you can make a conformal transformation of the coordinates and get an extremely simple model, which is even boring, such that potential u equals to 0, and potential v is even simpler, so it's constant. For that guy, this quantity c is the same stuff x plus x minus, which was on JT, but instead of quadratic term, you have a linear term. Well, so the symplectic leaves are paraboloid, so there is no chance to move. So that's, again, so that's, since they're paraboloids, all this you can take for C positive and C negative, you can find horizons, so they all contain horizons. Well, but of course there is just no chance to map, so the symplectic foliations looks very much different for the JT, and it's actually not movable, but it's possible just to take a part of JT. So the leaves which have, no, sorry, nothing is possible here, forget it. Well, so this model, yeah, unfortunately doesn't work. Now a simple example where it does work. So this model, which was used by Ed Witten some years ago for different purposes. So this model contains v which is minus x, which is exactly the JT, but there are also perturbations. So there are parameters which are just numerical parameters, and this is exponential stuff. So if yeah, in certain region of the value of x, it's very close to JT, but then it exponentially diverges. So for that model, so it's exponent, so you can integrate the Freund-Euler function, you can find the symplectic leaves. And so what happens if this beta here is negative, then independent of side of alpha, this model is completely equivalent to JT. So these perturbations really work because, well, these perturbations do not work for positive, since the model is completely different, but for negative, you're always staying in basically the same model. So it doesn't matter what you do with this parameter beta, as long as it is negative, this is all globally JT. So it's just the same guy. Other things, well, now let's go to Euclidean GT. What happens there? So the Casimir function now reads like that. So you have two Euclidean components, x1 and x2. So the Casimir function is just, it's again the usual Casimir of SL2. It has also symplectic leaves. Again, they are hyperboloids because this is just renaming of coordinates. But horizons now correspond to x1 and x2, 0. And therefore, so they also exist for various types, well, for some signs. So for positive C, it's a two-sheet hyperboloid which contains horizon point. For C negative, yeah, it doesn't because there is no solution. Then x plus equals to minus. So we can do the same stuff with Euclidean JT. It differs just in details. But it's a bit easier, so Euclidean gravity is a bit easier than Lorentzian one. And now, so that's, probably the most interesting, more general example. So there is a family, two-parameter family of potential U and V, which has a property. So for all that potential, so A and B are just constants. Okay, thank you. For all values of U and B, you have not only formulas for the integrals, but these formulas are basically very simple for elementary functions for the whole geometry. So this is a very good toy to play with. But besides of this family contains almost all physically relevant models. So okay, Daniel, let's do the same calculations. Let's analyze the structure of symplectic leaves and see which of these models have interesting holographic properties in that sense. Again, it's well, you just draw the pictures on the paper, and happens that you have some restrictions on the parameter. Well, they're written here. They don't tell you much. But what is interesting that this correspondence exists for what is called spherically reduced gravities. So if you take an Einstein gravity in d dimensions, d is larger or equal to 4, and make a spherical reduction, then naturally you will come into some dilaton gravity, and this dilaton gravity belongs to these regions. CGHS without conformal transformation, so full dynamical theory with black holes, is also here, and what is called Witten black hole. So most of the relevant examples, due to that result, actually admit you, well, first of all, Schwarzen as an asymptotic action, and therefore they are, well, these quasi-classical limits of SIK, but not globally. So we are kind of taking parts here. We're taking part of this theory which corresponds to just one side of that constant and map to it some part of the JT. So, well, and now just a very much toy example. It is kind of a joke. So in this context, you have one form which is spin connection, one form which is Zweibein, and another Zweibein. So we have three forms. And instead of making something fancy, we can just mix them up. So we just can take Zweibein and call this connection. This is the diffeomorphism, which change coordinates. And it happens that these maps, this is a globally defined diffeomorphism because no problem we are still naming the coordinates. And this maps Euclidean JT to Lorentzian JT. So the Poisson diffeomorphism in this sense is a weak rotation. Although you don't rotate the metric, you exchange the roles of spin connection with the role of Zweibein. I'm not sure that this is important, but this is amusing. This is definitely right. Well, and I think is basically all. So what's next? The next topic, of course, is to go quantum. That's where it becomes even more interesting. In perturbative regime, it's going to work. Yeah, because we are staying infinitely close to solutions. You expand around solutions, and I don't expect many problems, except that the right path integral measure is not defined by Poisson sigma model. It's defined by the gravity. So it has to be invariant under diffeomorphisms and Lorentz transformation, not under Poisson stuff. So there might be an anomaly. I don't know what does it mean, but usually anomalies are interesting. We are telling you something. And another point, so I never told this. So another holography for two-dimensional gravity, interesting stuff, is equivalent to matrix models. And this correspondence is not perturbative. So it's a funny stuff. So when you cut trumpets, you glue them to spheres, and you do all that stuff. You do this in the same model, but here it's quite possible that the trumpet will belong to one model and the sphere to another. So yeah, I don't know what will happen. Sorry. Thank you.
We have a few minutes for questions or comments, discussion. Go ahead.
Microphone also. Yeah, so I got a bit confused. So is there any connection between leaves and the space-time and in the de Sitter space? And what are the horizons? What's the meaning of the
No, the horizons, it's the following. So that's, I didn't write this formula, it's a little bit long, but you can think of leaves as classical solutions. So that basically they are classical solutions. So this C equals to constant, it defines a leaf, it also defines a classical solution. And by gauge transformation, you can basically reach any point on the leaf. There are some specific points which I didn't show, but it really shows that where this x plus or x minus equals to 0, this is horizon. This follows from explicit formula for the metric, which is basically, well, it's C minus whatever. So it is the conformal factor on the metric, so when the metric becomes degenerate where they are. So I didn't show you the geometry just because I needed very little information from the gravity side. All the game was in the Poisson manifold, so I needed just the structure of symplectic leaf and position on the horizon. That's what all. But there is one-to-one correspondence, so you have symplectic leaves in a model, you write a metric.
Okay, wait for the mic.
Yeah, very interesting, thanks.
Thank you.
I wonder how much you know about the degrees of freedom at the boundary, and I mean, coming back to this Go quantum, I mean, since you have this nice symplectic structure, you could imagine doing some deformation quantization, and, you know, based.
Oh yeah, that was, yeah, thanks. Yeah, thanks. It's, yeah, that's a very good thing. So I actually worked on differential quantization for some time, but unfortunately these two parts of my life never came together. The problem is in the following. So the people who were doing deformation quantization and some subsequent paper by people in Zurich, they considered the boundary conditions which were good for them. Good for them, this formalism did work. Their formalism did work because they had very few degrees of freedom. So they were able to even with a boundary, maintain structure of more or less a topological theory. So topological theory in their language means that practically no degrees of freedom, just some global information. But we need something different, we need these degrees of freedom. From time to time, I am trying to transform bound to an error, but I didn't succeed so far. So I don't have scientific method, and well, try and run doesn't work.
You mentioned in the beginning the flat space version. How does that fit into this classification scheme?
Yeah, great question. So that's, well, first of all, in 2D gravities, there is flat holography, which gives you warped Virasor as a holographic dual. So that's, but it's done by different methods. Here we have very different, so CGHS, which I mentioned, is asymptotically flat gravity. So we have a different holographic action. So that's Schwarzschild, which was for the case of flat space holography, or genuine flat holography. There was also Schwarzschild, but of a different group. There was a group of warped CFT, and here you have Schwarzschild of just of Virasor. So they're different guys. So there was no central extension in the Virasor part, there was central extension in the other guys. So we're completely different. Yeah.
Okay, last question.
Are you claiming that essentially everything is JT secretly, or everything is the Schwarzschild? Well, I can understand that in the bulk you can do transformation, but the Schwarzschild needs specific boundary conditions, and your boundary conditions have been mapped around.
Yes. Yes, more or less that. So that's, I would say, it's, well, it's all continuous space of models, but more or less it works in the half of a model. So if you just take one of them, it's either dinosaur on the street or not. So it either works or not. And it's more or less 50% of the cases. Right. The only point is that may work not for the whole target space, but just for the half of target space. Let's say you can map all black holes to, all spaces with horizons to all spaces with horizons, but the rest somehow doesn't match. That's a typical situation. But usually it works at least for a part of solutions.
All right, so in view of time, we can end it here. Let's thank Dmitri again.